So what we're going to do is we're going to try to figure out what the change in entropy, delta S, is quantitatively. It turns out that different ways of doing this. One way of doing this is if we know what the entropies are, final minus the entropies initial, the absolute entropies, we can do it that way. But we have to be able to determine the absolute entropies. Need the absolute entropies. The absolute entropies, they can be determined. The absolute entropies can be determined experimentally. Another way of determining delta S is via calculation, with a more theoretical calculation. And it turns out that delta S is also equal to K log base 10 W. And so we could do it based on a calculation. This is called the Boltzmann equation. And that's what we're going to look at first here, 13.1, entropy of the Boltzmann entropy. So let's look at the Boltzmann equation. Let's go straight to the equation first. This is S, the absolute entropy. Okay, so S can be determined experimentally, the absolute entropy, or S can be determined by calculation, or this is more theoretical. And so if we have this equation, K sub B is just for Boltzmann. There are different K constants out there. We'll see for reaction rates we use K as well. But that's going to be much later, so I'm not going to bother putting the B on there yet. But here's Boltzmann. And if you look at his tombstone, take a look at the equation that's engraved on his tombstone. S is equal to K log W. And so that's the Boltzmann. And so what can we do? Well, we can figure out what the absolute entropy is as long as we know what K is. K is very easy, because if you know R and you know N sub A, then you know what K is. In fact, K is the particle equivalent of R. R is in terms of moles. You know, R is the gas constant, 8.3145 joules per mole Kelvin. Now, if you take that number and divide it by Avogadro's number, N sub A, then we get K, which is the gas law constant per particle. So you just take R divided by N sub A, and then we get K, which is this. So K is no problem. W is a bit more complicated. W is the number of ways that you can arrange something. And the more ways you can arrange something, you know, then the higher the entropy. And the reason is because things can get quite disorganized, you know, if there are a lot of ways of arranging stuff. Versus if there are a limited number of ways of arranging things, then things are quite organized. For example, this book belongs on this part of the shelf, not that part of the shelf. Whereas if you put, like for, I just heard an example about librarians. You know, they're talking about how great, it was on the radio, they're talking about how great I think it was the New York Public Library system is. And they're saying, you know, if you just took 10,000 books and threw them on the floor, right, then there are no constraints. I mean, you just throw all the books up on the shelf. It doesn't matter where they go, you know. It's a lot of different ways of arranging the books. So entropy is quite high. Versus, you know, they're talking about how they organize the books and this kind of stuff. And that means there's a limited number of ways. You know, these books belong in this section, those books belong in another section. So things become quite a bit more organized. The number of ways of organizing the books goes way down, and the entropy goes way down. And so, again, the higher the entropy, the higher the measure of disorder. The lower the entropy, the more ordered things are. And for example, if there's only one way, so you know, this book has to be perfectly aligned in this position, and if it's off by, you know, an atom's width, you know, it's not acceptable. Well, if there's absolutely only one way of arranging it, then what is the entropy there? You know, if there's only one way of putting that book on the shelf, and it has to go that way, you know, and it has to be precisely that way each time, then if we only have one way, then the log of 1 is 0, which means the entropy is 0. And we see that in the case of a perfect crystal. A perfect crystal, there's only one way of arranging atoms. This would be like the perfect library. You know, the perfect library, the librarian's mind would have each book in its precise position where it's supposed to be. And that would be it. Except, you know, that only works at 0 Kelvin, because at higher temperatures, the atoms start to vibrate. And if they start to vibrate, then their position changes. So this is like somebody moving the books around a little bit, you know, back and forth. That would be, that would increase the number of ways and increase the entropy. And so it's only good at 0 Kelvin, because in that case, there's only one way of arranging it. The W, the waves, is called microstates. It depends on how many microstates you can arrange things in. And the number of microstates, you know, can be shown. Oops, I passed it. Because this goes through microstates first. You know, so if all the, let's say, if all this is an energy, and what you see here are a continuum of energies or quantized energies. These are quantized. You can see these are quantized because each line represents an allowed energy. So this is allowed, this is allowed. But if there are no lines here, then those energies are what we call forbidden energies. And so when we look at this one, how many ways are there arranging? Well, there are 5. And all 5 of those have the same energy. So if all 5 of them have the same energy, there's one way. But what happens if we increase the temperature? If we increase the temperature, then there are more, because if we increase the temperature, maybe we have enough energy to pop one of those up in higher energy to what we call an excited state. This would be ground state. And so, well, we pop one of the 5 up there, but, you know, and then these are color coded rather than calling it 1, 2, 3, 4, 5 or whatever. We'll pop up this one here. I think that's supposed to be red. Or, actually, we didn't have to pop up that one. We could have popped up the orange or the yellow, the green, or the blue. And so, altogether, in order to have this particular energy state, there are 5 different ways of arranging it. So those would be 5 microstates. In fact, you've seen this before. You've seen this before because you know, as we get to higher and higher temperatures, what's going to happen to the population? The population is going to shift up to higher energies, right? And so what we can do is we can tilt that on its side and then plot, rather than plotting this out with the balls, we'll call it population on the y-axis, and then we'll plot energy, as we go, increasing energy to the right. And so if we see something like this, we'll do it at 25 degrees C. At 25 degrees C, that's not 0 Kelvin. If it's 0 Kelvin, everything would be at the lowest energy. But at 25 degrees C, we're going to populate some of the higher energy states. Are we going to populate some of the highest energy states? Well, a little bit, but not much. The higher the energy we go, the lower the population becomes. And so let's say at about 25 degrees C, what we're going to see is this. It's going to be more populated. Let's see if I have it here. It's hard to see. But we can start having more. Do you see more energy states? At 25 degrees C will populate these higher. Well, do you know what this kind of distribution is called? This distribution is a Maxwell-Boltzmann distribution, or Boltzmann thermal distribution. It just shows the population of energy states depending on temperature. If we increase the temperature, the population is going to shift to higher energies. That population shift is going to look like this. So this would be at T greater than 25 degrees C. Populate those states. If we decrease the temperature, then the population shifts to lower temperature. And so we populate the lower energy state. The total population will stay the same. Because this would be at a temperature lower than 25 degrees C. You remember seeing curves like this? Where did you see curves like this? In which chapter is that? Kinetics, well, not kinetics, but kinetic molecular theory and kinetics, because kinetics, you see this although we haven't talked about kinetics, you see this in kinetics because if you have a bunch of molecules at 25 degrees C and there's a certain amount of energy required for reaction, then this might be what we'll term the minimum energy required for reaction. But you probably saw this more in chapter 6. In chapter 6, when we're looking at kinetic molecular theory of gases, let's just go back and take a quick peek at this. This distribution can be measured. Except this was the speed distribution. Well, speed and energy are related. You think about the translational kinetic energy of Newton's law of 1/2 mv squared. Speed. But this is the population distribution here versus speed or energy. We can measure this by, we can see how the population distribution changes with temperature. This would be a higher temperature. Mid-temperature, this would be a lower temperature. Actually, this would be lower and even lower temperature here. And then, of course, this can be measured as well. The way they measure it, let's see, is by measuring the populations individually. And so they have these rotating discs here that they can filter the population. So only certain speeds will pass through and measure how many pass through and plot this out. And so here we see experimental determination of that distribution. Well, this distribution this. And so let's go back to chapter 13 here. We use this distribution for a bunch of different things. We could use this for entropies, use this for kinetics. Kinetics is the speed of reaction, etc. All right, so let's continue on. But, it's likely that we aren't going to do this. It's likely that we really aren't going to count the number of ways, because if you think about it, You know, do we just deal with 5 particles? Over here, this would be 5 particles. In a chemical reaction, are we dealing with just 5 atoms? No, how many atoms are we dealing with? Typically moles, you know, Avogadro's number. And so do you want to count the number of ways there? No, you don't want to count, but you know, we could use statistics to help us so we don't have to count it individually, right? We're trying to figure it out. But still, it's kind of a horrendous task, because if we're just dealing with a mole, and this is very simple statistical kind of analysis, or this is probably for an ideal gas, you know, particles, a mole particles. Particles don't have any geometry to them. I mean, they can't vibrate or rotate just a single point in space. When you look at the number of waves for a mole of particles, the number of waves is 10 to the 10 to the 23rd. You know, that's enormous number. I mean, I don't think, is this even right? Okay, it's 10 to, you know, 10 to the 23rd. 10 to the 23rd would be, you know, 1,000 million, what is that actually, billion, trillion, 1,000 million, billion, 100 billion trillion, 10 to the 100 billion trillion power. It's mind-boggling, the number of waves. And so it's not like, you know, even a library with 10,000 volumes, you know, and you figure out all the ways, you know, that's much more manageable than something like this, because if you figure out all the shelf space and, you know, each book can occupy that one particular space, you know, it's huge. So anyway, if you were to count this, you know, and that's always the thing, if you were to count this, it would take you 3 billion years. Complete. It's kind of funny. So, what are we going to do? Well, what we're going to do is we aren't really going to use the Boltzmann equation. We'll use it for certain things. I sent a couple of homework problems with it. I'll post those later today. But, you know, here they're looking at microstates. So the first part of this chapter looks at the microstates and counting the number of microstates that are possible, you know, for different scenarios. But what we have to realize is we don't just work with very tiny sample. We work with a significant number of atoms and molecules. So how are we going to do it? How we're going to do it is we're not going to do it by calculation. We're going to measure the absolute entropy. Now, how do you measure the absolute entropy of something? And it turns out this is where we're going to go to, you know, Clausius, actually, equation here. And so let's take a look. Clausius' view. With Clausius' view, we can do this here. And this is at 13.2 here. And so I said we can do a calculation, but that calculation is going to be horrendous. And so what we're going to focus on is experimental determination of this. When we look at the experimental determination of the absolute entropy, well, actually, that's not the absolute entropy, that's ds. You know what D stands for in math? ds, D. You guys know what delta stands for. Delta stands for change. Well, D is a small delta, and a small delta, it just means a very, very tiny change. Yeah. And so, you know what, I'm not going to use ds, I'm just going to call it delta s. And so we're looking at a change in the entropy here, not the absolute entropy, right, but a change in the entropy. Now, delta S is equal to, okay, dq reversible over t. So we'll have something like this. dq reversible over t. Essentially, this is what we're going to do. We're going to use some calculus. I'm not going to get into calculus because calculus is beyond the scope of this class. And what we're going to do is we're going to relate this, when we think about this dq reversible, this is, we can relate to heat, changes in heat. When we're thinking about heat, the heat, some things can absorb a lot of heat, some things don't absorb much heat. Water, water is very interesting because water can absorb a lot of heat. How come it can absorb a lot of heat? Well, there's a lot of ways that water can absorb energy. What are the ways? Well, there's hydrogen bonding interactions we can break. There's vibrations of the water molecules that we can make. There's rotations of the water molecules. There's translations of the water molecules. And so water is a good heat sink compared to something like copper metal. If we're looking at copper metal is not such a good heat sink. There aren't a lot of ways that copper metal can absorb heat. Pretty much if I have copper metal, it's just going to vibrate, and that's it. And so what we say is that water has a high heat capacity because high capacity to absorb heat, whereas copper has low heat capacity. It doesn't have much capacity to absorb heat. Well, this term in the numerator, we can relate to heat capacity. There are different kinds of heat capacity. If we go back to chapter 12, not chapter 12, chapter 7, and look back at the types of heat capacities that we dealt with, what are the different types of heat capacity that we have? Heat capacity is just a general word for the relationship between heat, Q, and temperature, T. But the types of heat capacity that we dealt with were specific heat. Specific heat, the only difference between the types of the units, specific heat has specific units. The units of specific heat are joules or calories per gram degree C. But there's others. There's molar heat capacity. Molar heat capacity would have units of joules per mole per degree C. And so a lot of people think only in terms of specific heat, but we can't, because there are other types. It could be per mole rather than per gram. And then there are other heat capacities. For example, if you're building a brick wall and you want to figure out the heat capacity of the entire wall, would you weigh out how many grams of brick you have? No. Would you weigh or would you calculate how many moles of ceramic, earth, whatever makes up those bricks? No. And so the other type of heat capacity is the heat capacity of an object. We use heat capacity of the object for calorimeter. When you do calorimetry, how many calorimeters do you use? A gram of calorimeter? Do you use a mole of calorimeter? Or do you just use one calorimeter? Well, we just use one calorimeter. So the final units of heat capacity would be joules per calorimeter per degree C, or just joules per degree C. And so we can relate it to heat capacity. And if you go back to chapter 7, you'll see there's lots of different heat capacities. And so we use some calculus to get us to this point. It's going to take us to this point where we go S final minus S initial is equal to this symbol here, the integral heat capacity to different temperatures. And so all this equation says is that we take this, which is called an integral, which is essentially just the area under the CP versus T curve, 1 over T curve. Essentially, what it's going to look like is something like this. If I want to figure out the change in the entropy, it's going to be, I have to figure out what my initial entropy is here, and the final entropy. I can do this by looking at the temperature, the initial temperature, and the final temperature of this. In other words, what I'm going to do is I'm going to measure the heat capacity at different temperatures. And so an example of this would be water. If I do H2O, and I start measuring the heat, what is the heat capacity of water, by the way? Do you know? 4.18. That's the heat capacity for liquid water. 4.18 joules per gram degree C. Since the units are joules per gram degree C, we would call it a specific heat. Does the specific heat of water change with temperature, or does it stay constant? Is it 4.18 at 4.5 degrees C and 4.18 at 99.5 degrees C? Is it the same? No. It's not the same. The specific heat changes. And so if we're looking at the specific heat of water, it's a little bit different depending on where we are. And so, but we can measure it. You just change the temperature and measure the heat capacity at that particular temperature. So we can do that. We don't have to, if you go back to chapter 7, we could calculate it too. We could calculate it, but what is that calculation based on? So if we go back to chapter 7, and we look at specific heats and temperature, then we could see. This is chapter 7. So for example, here, on problem number 118, here, what is this? Talking about, strictly speaking, the heat capacity of a substance at constant pressure is the slope of the line. Okay, some thermodynamics type stuff here. Go down. Heat capacity is just this change in enthalpy or change in temperature. This change in enthalpy is usually Q over change in temperature. But we can continue on. This is a similar equation that we were looking at earlier. But let's continue on down here. On the other hand, we often find that the heat capacity is a function of temperature. A convenient empirical expression is the heat capacity is equal to A plus BT plus C over T squared. T is the temperature. What are A, B, and C? A, B, and C coefficients. Where do we get those coefficients? And so this is an empirical expression. So what does it mean, empirical? Empirical equation, empirical expression, empirical law. Empirical is a very common word in science. And, what does it mean? Empirical. Well, no. Yes and no. This, would I have to go in and measure? Would I have to measure these using calorimetry? Yeah, I'd go in there and measure. So I set the temperature. Maybe I'd change the thermostat in the lab so I don't have to heat up the water to make the room hotter and hotter. And let the water equilibrate with that. We'll measure the heat capacity. No, what it is it boils down to this kind of the two-pronged approach in science. What do I mean by two-pronged approach in science? Or you probably never heard of a two-pronged approach in science, right? Have you ever heard of a two-pronged approach? What would be nice is, I don't want to have to do the experiment. I really would rather not do any calorimetry experiments for the rest of my life. I'd like to not do any calorimetry experiments. I would just much rather just be able to calculate it, right? And so if I could just go ahead and calculate, what would I calculate it from? like, I would calculate it from, well, this is the two-pronged approach. I would calculate it from what? One prong is observation, experimental facts, just observations. The other prong is theory. I just calculate from theory. And so does empirical mean that this equation came from the theory, that somebody just figured that out theoretically, that the specific heats will change in this fashion? No, empirical means just the opposite. Empirical means it came from experimental data. It came from observations. And so what somebody would have done is somebody would have gotten some experimental data and then tried to fit this to a mathematical function. And the mathematical function they came up with is this, where it's a negative second order temperature here. It's a very funny equation, right? You have to be very careful because you don't just want to do one prong. For example, if I have a cup of coffee here and I measure its cooling, right? The problem with doing everything strictly empirical is this. If I measure the cooling of my cup of coffee, I'll take a measurement here, and take another one here, and then another one here, and then another one here, and then another one. And so this is cooling down, right? But the next thing is I want to fit this. I'd like to fit this to some mathematical function. And when I fit the cooling of my coffee to a mathematical function, it looks like it's going to be like a third or fourth order mathematical equation because it looks like it cools down here and then warms up here and then cools down again and then cools down again, right? And so my coffee is doing this. It's cooling down and warming up and cooling down and warming up and then cooling down, maybe warming up and warming up. Is that really the case? Even though mathematically I can fit this data using some high order, like higher and higher order, but does it make any sense that, if you have a cup of coffee, is it really going to warm up? Or is it just going to cool down? It's just going to cool down, and these fluctuations that we see are a result of what type of error? Is that, well, there are two types of error that we usually worry about. What are the two types of error that we're concerned with? We're concerned with, I know this is way back because this is chapter 1. I'm not going to flip back to chapter 1. It takes me too long to flip back to chapter 1. But what were the types of errors?
What, round off error?
Well, okay, round off is that's a type of error, round off error. But experimental data is subject to two types of error. Round off error is just based on calculations, somebody overzealous or not enough precision in the experiment. One of them starts with R. Random error. Right. This is usually due to random error, these fluctuations in the data. And so even though we might fit this to some weird polynomial mathematical equation, that mathematical equation is not accurate because we have to think about the physics. We also have to think about the theory. We can't just do strictly math because if we do strictly math, this doesn't make any sense. So what we do is we just say, the cooling should be a nice, smooth function, and then fit this black line to it. Or we think, we have to get the black line here, and we're going to assume it is this nice, smooth function. And so these fluctuations are due to random error. So we have to also think a little bit in terms of theoretical as well, because you can fit any data with higher and higher order polynomial equations, no matter what, but it might not make any physical sense. The more adjustable parameters you have, the less. And so this has quite a few, but it probably fits it okay. If you look at this, these are the numbers. These are empirical, constants that come out of the equation. This is just like solving for the slope. you know, if we have a linear line, we just solve for the slope, and the slope is what makes that equation fit the data. But this is not water. This is, what is this for? Nitrogen. This is the molar heat capacity of nitrogen. And we can see the molar heat capacity of nitrogen gas. This is just gas. Changes a little bit with temperature. How about water? Water. Eric probably remembers this because I signed this as homework from, or maybe you, do you remember this problem?
Yeah, I think so.
Okay, 119. Yeah, this one is for water, you know. And so how much heat is required to convert 10 grams of ice at -5 degrees C to steam at 100 degrees C? The temperature-dependent constant pressure specific heat capacity of ice is. And so ice is normally taken as 2.01 joules per gram degree C, but it varies a little bit. And so when we look at the temperature-dependent, it comes out to, well, it's just 1.01 87. So it's a linear function. It's t, and so it varies linearly with a positive slope here, negative intercept there. And so the temperature-dependent heat capacity of ice is, and if you look at the slope is close to 1, so it's pretty much a flat line. It's pretty constant, right? And so it doesn't change much. But when you look at the temperature-dependent constant pressure specific heat of water, take a look at this. This is negative 1.0 times 10 to the minus 7 T cubed. And so this would be AT cubed plus BT squared plus CT plus D. You know, that's a third order polynomial. And so there's some funky stuff going on with the water, you know, and this is the, well, where did this equation come from? Does this equation come from theory? No, this equation came from the experimental data. And so I'm doing water here, and I'm looking at this, and if I look at these data points were fit mathematically with this function, but I'm not going to use this function to calculate these, because that's the reverse order. This equation came from the experimental data, not vice versa. You know, these data points here did not come from theory. Now, if this, you know, if this, we would call an empirical equation. Empirical means it came from the actual experimental data. If it came from theory, what would we have called it? You know, or when things are determined from theory, you know, we have different names for these types of things, you know, because in different grades. So if something comes purely from theory, then usually that's called like ab initio, you know, ab initio, like calculations or theoretical calculations. And so you could have purely empirical, which would be, you know, this, or ab initio, which would be the theory, or you try to meet somewhere in between, you know, not one or the other, but somewhere in between. Somewhere in between would be not the rigorous calculation, but it would be more like semi-empirical or a whole host of other types of calculations. And so for this, what we do is we don't do any math, we don't do anything, we just collect the data. So change the temperature, measure the heat capacity, change the temperature, measure the heat capacity, change the temperature. And so you do this. And so what we want to do is this, though. If I want to figure out the entropy of water at 25 degrees C, then I need some initial entropy to start off with. And so how am I going to get that initial entropy to start off with? The initial entropy is a challenge, except we know something that makes it a lot easier. If we say the initial entropy is the entropy at 0 Kelvin, if we say that, then what happens is this initial entropy is we're going to use the third law of thermodynamics. The third law of thermodynamics, and we'll set it equal to 0. And so what we're going to say is that the initial entropy is going to start at 0 Kelvin, and that entropy is going to be 0. And so we don't have to measure, you know, we don't have to measure the specific heat all the way to 0 Kelvin. In fact, is it possible to measure the heat capacity at 0 Kelvin? No. You know, how close can we get to 0 Kelvin? Pretty close, but how close can we get there easily? You know, it's pretty easy to get to what temperature without too much difficulty. Without too much difficulty, you can get to,
In the lab or in general?
in the lab,
I think 2 degrees or something?
in Kelvin.
Yeah.
Yeah. Do you know what is an easily achievable
extremely low temperature in Kelvin. We can easily get to 4 Kelvin. What's special about 4 Kelvin?
Liquid helium?
Liquid helium, exactly. So liquid helium is very special. In fact, I used to have to use liquid helium. Did I talk about this last time?
Well,
A little. Because I was working with superconducting magnets. This is like, you know, like in MRI machines or the smaller version, NMR machines, they have these superconducting magnets and, you know, the coil that needs to be cooled down to low temperature. Not quite liquid helium temperature, but colder than liquid nitrogen temperature. And so the liquid helium would usually have to be refilled weekly. And so some guy would come in and pour in. It's kind of weird how they put the liquid helium in there, but they flush in liquid helium in there. And then since I didn't do liquid helium, I was on liquid nitrogen duty, so I'd have to put in liquid nitrogen. And so what you have is liquid helium in the core, and then liquid nitrogen surrounding that core. Liquid nitrogen's a lot hotter, a lot warmer than liquid helium.
Anyway, you do heat capacity. So this would be H2O liquid here. And then when we get, you know, H2O liquid is around 4.18. And then when we get to H2O solid, it's way down here, right? H2O solid, ice, here. And then you can't measure all the way down to 0, but what you can do is you can just extrapolate. You just assume that the, so we don't have the data here, but you can kind of assume it doesn't fluctuate like, you know, coffee warming up or cooling down. And so we just have a smooth trend out to here. And so this is the value of the third law here. The third law is going to allow us to determine the absolute entropies here. And so what we're going to end up with is S final. S final is just going to equal this. And this is the area under the heat capacity curve. So we'll just do it this way. I'm just going to plot it like this. And so, for example, if I want the entropy of water at 25 degrees C, I go to 25 degrees C here. There's a big drop. Here. And then I would just figure out the area under here. Starting 0 and going to T final, which would be 25 degrees C. And this area would be the entropy of water at 25 degrees C. And in fact, I could determine the entropy at any temperature if I have the data. So for example, if I go to H2O gas, H2O gas is going to have a higher entropy or a lower entropy than H2O water. It should have a higher entropy, but it's H2O gas specific heat is actually lower. The specific heat of H2O gas is lower than H2O liquid. H2O liquid has usually high specific heat. So if I go to H2O gas, it's out here. Gas like that. But what we're looking at is we're looking at the area. So we start off at 0 and we end up at, let's say, over here, you know, some very high temperature. And this would be the entropy of that H2O gas. And so, you know, that's a lot of data because that's the entropy of water over a wide temperature range. And, you know, just water alone, there's going to be a lot of data there. And so what we want to do is we want to reduce the amount of data. The way we can reduce the amount of data is come up with mathematical equations describing this, you know, this kind of function. If we have mathematical equations, then we don't need a big data table. But we don't have a mathematical function that's going to be describing this that we're going to use. In fact, we're just going to collect the data. Well, if we're going to just have the data as in a data table, then do you want, at what temperature do you want to know the entropy of water? Yeah. You know, what do you think would be the most useful temperature to know the entropy of anything? You know, or what's the most common temperature you do chemistry? You know, the temperature fluctuates, like sometimes it's cold, sometimes it's warm. Right now it's 68, that's a little on the cool side.
But if you're going to pick a temperature, what would you do? Would you pick 0 degrees C? Would it be the most useful? No. Probably the most useful temperature to know entropies would be at 25 degrees C, room temperature. And so what we want is we want the entropy at 25 degrees C, but what about all these other entropies? Well, all the other entropies are going to not necessarily deal. And so we're going to compile those. And where are we going to compile them? We need, well actually, you know, we want a lot of entropies for a lot of different things. And so we'll have to compile these in not chapter 13. We're going to compile these in appendix D. Let's take a look at appendix D. So looking at appendix D, you can see here, first column is entropies of formation. The second column we'll talk about later. The third column are the absolute entropy. You see, this is just S. It's not delta S. Like, this is delta H. It's change in entropy. This is just absolute entropy. This is the heat capacity. You know, typically the higher the heat capacity, the more ways that this can absorb energy, and you expect it to relate into higher entropies. So the heat capacity at, well, what temperature are these entropies? Because the entropy does vary with temperature. And so what temperature are these entropies at? Multiple temperatures or just one temperature? Just one temperature. Which temperature is that? 298.15 or 25 degrees C. Now, what if you want the entropy at a different temperature? Well, it's not going to be on this table. You're going to have to look at it in another table. So you won't find it here. And so, anyway, let's take a look. So, for example, when we look at a table like this, we want to familiarize ourselves with the table. So we look for things like the spread, numbers. And so just to get familiar, we would probably want to know the smallest entropy, the lowest entropy, and the highest entropy, right, on the table. And so let's scan the table and look for the lowest entropy. And so this is a start aluminum 8 for aluminum 23, minus 321.7. That's pretty low. So keep that in mind, minus 321.7. Do you see anything lower? No, not yet. I'm just going to go. Okay, we'll go to the next page. Minus 73.2. No. 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 99.6, negative 99.6. No. Minus 315. What is that one? 321? Minus 321? Minus 315. Close. Not quite there. Iron 3. Minus 222, phosphate. Minus 222. Looks like iron 3 and phosphate came close, but not quite there to topple it. So looks like that's it. We scanned the entire table, 5 pages of it, and so it looks like aluminum 3 is it? Minus 321.7. Is that strange? Minus 321.7. You have to think about that.
You have to think about that because what's the entropy of a perfect crystal at 0 Kelvin? 0. So that has the lowest, well, maybe that doesn't have the lowest entropy because this is an even lower entropy than 0. And so that means that this must be what they call an exceptional specimen of a perfect crystal, you know? Or maybe this must be a super perfect crystal, not just a regular perfect crystal, but a super perfect crystal. Is that right? Or maybe that's a typo. Maybe they must be mistaken because if I count the number of ways, you know, what do you think? Is it typo? Screwed it up? Because if you have a perfect crystal, there's only one way of arranging things. And then, according to Boltzmann, the more ways of arranging, the higher the entropy becomes. But what we want to do is we want to go down. And so we're starting at 0. We need to go down in entropy, which means that there has to be negative ways of arranging. Rather than positive 10 ways of arranging, there are negative 10 ways of arranging. That is, you know, you're going to be in debt because there's not enough. Is that right? Your deficit. Dearth of ways. No. And so does that seem like a little strange? Third law of thermodynamics says that the entropy of a perfect crystal has the lowest entropy of 0. And so how's that possible? How can we have a lower entropy than 0?
I'm going to say for ions, maybe solution is relative.
You're not supposed to read those kind of things, but you did. That's good. Yeah. You know what the reason is? The reason is for ions are super well ordered. Is that it? Let's see. For aqueous solution solutes, for data for ions in aqueous solution are relative to values of 0 for delta HF, delta G naught, S naught for H plus. And so we ran into the same scenario. The same scenario happened in Chem 1A. Eric, you remember it?
Not too well. I think there was one.
The same scenario happened because that's impossible. You know, the lowest entropy we can have is 0, right? And so how can we have a negative entropy? We can't have a negative entropy. And so we saw a strange entry in Chem 1A for delta H's of formation. Delta H of formation, it's good that you caught that, but the question is why? It's good. Most people don't even read these. Some people will use this the entire semester and never have once read this. It goes the same for the chapter too. A lot of people won't bother reading the chapter as well. But why is that? Why is the data for ions different than the data for everything else? And so this has to go back to chapter 7. The answer is in chapter 7. I don't know if anybody reviewed it, that part. But we see the other unusual entry here, and the other unusual entry is this. You know, and that is the delta H of formation of H plus. The delta H of formation of H plus, is it 0? No, it's not. I mean, this is the formation of H plus from H2. So if we take a half a mole of H2, you know, a half a mole of H2, this is a formation reaction. Half a mole of H2 gas goes to a mole of H plus aqueous. Well, the first thing is we have to break a half a mole of H bonds. How much energy does it cost to break an HH bond, roughly? It's ballpark. How much energy would it cost to break a mole of HH bonds? 200's on the low side. You know, 200 is almost visible light can do that.
You know, like violet light would probably be able to break that. So you got to be a little stronger to prevent that. And so 200's in the realm of visible light as far as energy goes. And so just go a little higher. Well, what is it? 210? What do you say is higher? 400. Yeah, it's about 400. And so we're looking at half a mole, so it's 200 kilojoules roughly. And so we break the HH bond, then we have to ionize. If we ionize a mole of hydrogen atoms, how much energy does that take? Ionize it roughly. Well, what's the hardest element to ionize? What's the hardest atom to ionize? No. Nitrogen's hard to ionize, but not the hardest. What's the hardest on the periodic table? Helium. Helium's the hardest. Hydrogen would be the second hardest. Helium's over 2,000 kilojoules to ionize. Hydrogen is like 1,500. And so, you know, we're approaching 2,000 kilojoules just to do this, to break the bond and then make the ion. But we're going to get some energy in return because, you know, ionization energies, bond breaking, this is for gas phase. What we're going to do is we're going to take the H plus in the gas phase and bring it into the aqueous phase. When we take H plus and bring it into the aqueous phase, what happens? You know, when you put ions in water, what happens when you put ions in water? Like lithium ions in water. What happens when you stick lithium ions in water? Does it become more stable or less stable? It becomes more stable because,
Aqua lattice, I think.
well, we don't call it the aqua lattice. We call it something else, but it's similar in a sense to that. We call it not aqua lattice. We call it kinda, you know, we call them ion dipole attractions. And these ion dipole attractions form a structure in which the ion's surrounded by sphere of water molecules. That's called like a hydration sphere or a solvation sphere. So we have solvated ion. The solvated ion, because of the ion dipole attractions, is going to help stabilize the hydrogen ion or hydronium ion. And so we get some energy in return, but net, we wouldn't think it comes out to zero, and it doesn't, in fact. And the question is why? Why do this? You know, in other words, this. The delta H of formation of H2 is zero. You know, because we're forming H2 from H2, nothing changes, there's no change in energy, it is zero. The delta H of formation of H plus is arbitrarily defined as zero. And so why did we need to arbitrarily define it as zero? This is back in chapter 7. And so tell me the reason why the H plus AQ is arbitrarily set to zero. The example they use in the book is HCl. Does that ring a bell? Anybody? No. Well, you know, this type of stuff, because I asked my morning class, I had some carryovers from Chem 1A in the morning class. Everybody forgot. Everybody forgot, even though, you know, I think, how many times did I mention this in Chem 1A? At least 3, I think. And then I realized, you know, I could repeat things, and people would go, okay, I'll try to remember that, but it's not memorable. You know, it's hard to remember. It's easy to forget. It's easy to forget because you're just memorizing what I said, and I said, you know, this is the reason why we have to arbitrarily set this to 0. Right? And so that type of stuff is hard. It's hard for me to remember that type of stuff too. I never remember that kind of stuff. And so the best thing to do is to remember it in your own words, you know, and then it becomes much more significant. it becomes something. And so what you should do, and this is what I used to do as a student. As a student, you know, I'd write down what the professor said, but every time the professor said something, I'd write my little annotations next to it. Okay, in my words, this is what he's trying to say or she's trying to say. You know, this is the point. Then I'd ask for verification. I'd say, is this correct? Am I thinking about this right? You know, and that's what you want to do. Well, the same thing here. You know, you should put this in your own words to try to make it more memorable. You know, why do we have to set this arbitrarily to 0? And so I asked you to review chapter 7. This is one of the things I want you to review. So I'm not going to tell you why it's arbitrarily set to 0, other than ask you to go back in chapter 7, read the paragraph or two that talks about why it's arbitrarily set to 0. But you can see the entropy. Now, in order to have an entropy of 0, that means everything has to be perfectly positioned. And is that the case for H plus AQ? You have 1 mole of hydronium ions or hydrogen ions in an aqueous solution. Are all the water molecules and all the H plus ions perfectly arranged to give it 0 entropy? Do you believe that? Absolutely not. You know, it's not like you're going to a library and then, you know, everybody's going to be in their perfect position. You go to the library, well, maybe at the beginning of the day, but, you know, this is at room temperature. Obviously not. You know, things are going to be moving around. That H plus might have been here, and then it's there, and then it's here. You know, it's not perfectly arranged, but then why does it have an entropy of 0? Why it has an entropy of 0 is the exact same reason why delta H formation has an enthalpy of formation of 0. It's the exact same reason. And so this brings up, hey, that's an error. That's absolutely an error. But this type of an error is not a random error. This is what we call a, what was the other type of error? Random error, and there's one other type of error. The other type of error is not a standard error, but it starts with an S. It starts with an systematic error. And what happens is this. All the cations are going to be systematically too low. They're all systematically too low. All the anions are going to be systematically too high. And what happens is, well, you can't form a cation without an anion, so what happens is they cancel each other out. So systematic error in one direction cancels out the systematic error in the opposite direction, and then it works out fine. And so we could just throw it all in the same table. But throwing it all in the same table is very tricky because this is like this. You know, I can ask a question like this. And in fact, Eric, I probably asked this exact same question on your test, Chem 1A. Actually not this. Chem 1, well, this would be Chem 1B. Let me ask you this. Which one has a lower entropy? 28.33 or minus 321.7? Which is a lower entropy? 28.33 or minus 321.7? Which is a lower entropy? Let me ask you this. What's a lower temperature? 28.33 or minus 321.7? What's a lower temperature? Yeah, you'd say minus 321.7, but you know, you could be wrong. You could be wrong because I didn't tell you one thing. I didn't say 28.33 Kelvin versus minus 321.7 Fahrenheit. If I said that, then you'd say, oh, well, actually 28.3 Kelvin is lower than minus 321.7 Fahrenheit. And so we have to be careful, and this is the point. Anybody can grab the values out of this table. Grabbing the values out of this table and plugging them into an equation is super easy. You don't have to know any chemistry. You don't have to understand the table. You just use the numbers, right? Well, that's like 99% of the people. 99% of the people, they just take the numbers, they don't know what the numbers necessarily mean. But this table is very tricky because in this table, and they don't label it because all the units are the same, but in this table, this would be like Kelvin, and this would be like Fahrenheit, maybe for the cations, and the anions would be like Celsius. And so what we're doing is we're mixing up all the temperatures in the same table. Well, you go, that's crazy. We don't want to put the Fahrenheit and the Kelvin and the Celsius temperature all in the same table. It makes no sense because we can't compare the numbers. But it makes total sense because of this. It makes total sense because we can compare the neutrals with the neutrals. So for example, aluminum with aluminum chloride, no problem. You know, which one has lower entropy? This one, for sure. 2833 is lower than 110, right? Because that would be like Kelvin, 2833 Kelvin versus 110.7 Kelvin. We can compare the cations with the cations, because the cations with cations would be like Fahrenheit versus Fahrenheit, right? And we compare the anions with the anions, because that would be like Celsius and Celsius. But why are they mixed up in the same table? They're mixed up in the same table because of the systematic error. You know, the systematic error in the cations would cancel out the systematic error in the anions, and therefore we'll just throw them all in the same table and expect you guys to be sophisticated enough to keep track of all that, right? But it's tricky because I'll ask a very simple question. Which one has a higher entropy? Aluminum solid or aluminum 3 plus AQ? And do you know, the last time I asked this question, on the test, a lot of people answer aluminum 3 plus AQ. Why? Because it's a lower number. But there's no way that's possible, you know, here. And so what we'll do is we'll just look at the neutrals first. And so if we look at the neutrals, and we're going to ignore the cations for now and the anions for now, but did you notice something? Did you notice something about the cations? In the anions, you know, which species gave you the extremes as far as the entropies go? There was a little pattern in there too. It was the higher charge species. The higher charge species are going to be lower than the lower charge species. They're going to be more ordered, as we saw. This Al3 plus aqueous, there's just some random aluminum ions floating around in water, and those ion dipole attractions with water molecules, you know, bouncing into the aluminum and that kind of stuff. Is that it? No, as you saw, there's a lot more structure in this. In fact, aluminum 3 plus AQ, aka hexa aqua aluminum 3 ion, is quite structured, quite ordered within that structure. And so we'll see that compared to something like a barium 2 plus ion. We compare that to a barium 2 plus ion. You know, barium 2 plus doesn't have that high charge density that aluminum 3 plus. Well, the barium 2 plus is not bad. It's still, but if you look at it, we can compare the cations with the cations. Which one's going to have a lower entropy? For sure, the aluminum 3 plus compared to the barium 2 plus. And so that worked there. But let's look at the neutrals and see which one's lowest. So as I can scan the neutrals, and I'm going to save time here because I'm not going to scan the whole table again. I'll just go straight to it. You know what's going to have the lowest entropy on this table? Right here. This is the lowest entropy on the table, diamond. Diamond's entropy is 2.38. It's close to 0. That means the atoms are well positioned at room temperature. Graphite's a little higher than that. I further scan the table. And when I further scan the table, I see most solids are between 0 and 100. It's the bulk of the solids, 0 and 100. Liquids are 100 to 200. Gases are above 200. Those are. We'll see some exceptions, of course. You know. So, for example, we could see an exception here. What's weird about aluminum sulfate? What's weird about aluminum sulfate? What's weird about aluminum sulfate is, you know, typical solids have entropies in the range of what?
0 to 100, and so this is over 240. That's a little high. And so for me, aluminum sulfate's weird because it has kind of a high entropy for a solid. Why does it have such a high entropy? Aluminum sulfate has a very unusual structure because you have the alumina ions, and the sulfates are tetrahedral. Tetrahedrals are like balls. And it turns out these sulfate ions can spin within the lattice, increasing entropy. And so it's very weird. Of course, if you cool it down, it will stop the sulfates from spinning, the entropy will drop down. This one has kind of a high entropy too. This dialuminum hexachloride. Dialuminum hexachloride has a kind of a high entropy for gas. That's 490 because the molecule, dialuminum, is a molecular compound, not an ionic compound. The molecule's kind of big, and so it can vibrate and rotate in different ways. And so that's it. But most of the other stuff falls in. This is ALF3, ALO2, O3. That's typical what we expect. There's one that you should be aware of. That's a little different, unusual, and it's quite common. And so we should take a look at it. So let me just forward here. Do you see it here? As far as entropies go, do you see one that kind of stands out as being a little different or unusual? Need some of these aqueous solutions are.
Water.
Water, yeah. If you look at liquid water and its entropy is 6991, which is comparable to a solid. And so what makes liquid water much more ordered than a typical liquid? If we look at a typical liquid, typical liquids are between 100 and 200. So if we look at sulfuric acid, pure sulfuric, it's between 100 and 200. So that seems typical. And so water is unusually ordered for a liquid because of its strong hydrogen bonding interactions. And that's going to keep the water molecules much more ordered, much more constrained than they normally would. Because water molecules can't just adopt any orientation because there are strong interactions between the water molecules. And so we can scan a table like this and get some kind of idea, some kind of feeling about entropy. The units of entropy are a little weird too, because the units of entropy are going to be joules per mole Kelvin. So it's a little weird. But we can see, of course, joules related to energy here. And Kelvin, temperature. Moles, just the amount. All right, so once we have a table like this, then the calculation is so easy. The calculation for calculating entropy changes, delta S is going to equal the sum of mu P, and this is not going to be delta S, it's just going to be S of P. We're going to do this under standard conditions. Standard conditions means what?
1 bar, right?
Actually, in this table it means 1 bar, in other tables it means 1 ATM. So for example, if you look at that chart there, that's in ATM there. Mars is going to be in bar. All right, so this is going to be the final entropes, that is the entropes of the products, minus the initial entropes, that is the entropes of the reactants. And these would be absolute entropy, reactants of products. And so let's do a quick calculation. The calculations are easy, just like the delta H calculations are easy. But the hard part is, all this thermodynamic stuff is understanding what those numbers mean. That's the hard part, because anybody can do the calculation, but not everybody, has in-depth understanding of this weird table here. And I always thought, it would be a lot easier because I wouldn't have to spend so many hours talking about this table in Chem 1A if they just separated into 3 separate tables. A table for the neutrals, a table for the cations, and a table for anions. The reason they don't separate it into 3 separate tables is because of the systematic error canceling each other out. And so let's take a look at this. Let's do an example here. We're going to do methane combustion. The methane gas, so 2 gas, CO2 gas plus H2O liquid. Now, we're going to look at energy and entropy. What's going to happen to the energy here?
If we have combustion of methane, is combustion of methane exothermic or endothermic? Should energy go down or energy go up? We go from reactants to product. Up? Up. So if energy goes up, that means we have to add energy to make this go. Do we continually have to add energy to combust methane? No. We have to give it a spark, initial spark, but once we give it the initial spark, then we don't have to add any more energy. In fact, it doesn't consume energy, it releases energy, meaning if it releases energy, it means energy is going down. That is, the system's energy goes down. If the system's energy goes down, all that excess energy is expelled to the surroundings. The surroundings are going to warm up. And so energy goes down. This should be exothermic. Well, we can calculate this. It depends on how we burn this. Should we calculate delta H or should we calculate delta U? Which one should we do, delta H or delta U? I'm just using E generic, but E stands for delta H or delta U. Well, it depends on how we burn it. How do you burn methane? If I combust a mole of methane, let me ask you this. If I burn 1 mole of methane in the open lab here versus burning 1 mole of methane in a bomb, like a bomb calorimeter bomb, would I get the same amount of heat? Do I get the same amount of heat if I burn this in a bomb versus burning it in the open lab? No. Do you know which one yields more heat? The bomb or the open lab? The bomb, you're saying?
Yeah.
Anybody else? How would I determine which one yields more heat? Well, this is what I would have done in Chem 1A. I would have done this. 25 liters plus 50 liters gives me 75 liters. 75 liters initial volume, final volume, 25 liters plus 2 moles of water. 2 moles of water is 36 milliliters, or about 0.04 liters. And so I go from 75 liters to about 25 liters. What happened to the volume of the system? The volume of the system goes down. If the volume of the system goes down, the volume of the surroundings goes up. If the volume of the surroundings goes up, the surroundings does the work. That means we're going to get more heat if we burn this in the lab because the surroundings will add energy to it by doing work on the system. And so it'll be more exothermic because of the surroundings. Whereas if we do it in the bomb isolates the system from the surroundings, so the surroundings can't add that extra heat, right? There's no work in the bomb. And so, anyway, what do we do most of our reactions in a bomb or the open lab? In the open lab, so delta H makes the most sense, delta H. Actually, there's one more thing I need to review, and this is something I realized that when I was talking to a student. When I was talking to a student, they conceptually got mixed up. They got mixed up because they're thinking about heat, temperature, etc. And so yesterday somebody asked me a question in the morning, or was it in the morning or the afternoon? It was in the morning. Somebody asked me a question in the morning about heat. Where did the heat go? We're talking about the adiabatic and expansion of a gas, right? Adiabatic expansion. Where did the heat go? Well, where the heat went into is this. When we think about heat, there are different ways. When we think about energy, there are different ways we think about it. Our system, I divided systems, into reaction process versus object. And so what they were doing is they're mixing up these two. I don't mix up these two. I keep them separate. I keep them separate because of the calculations. When I think about these things, I want to think about how I'm going to calculate it. And so in a reaction process, like for example H2O, I have H2O solid at 0 degrees C, and I heat it up. If I have H2O solid at 0 degrees C and I heat it up, what's going to happen? Well, it's ice. Ice at 0 degrees C. If you add heat to ice at 0 degrees C, what's going to happen? Now let me ask you, does the temperature go up? the temperature doesn't go up. And so we end up with H2O liquid at 0 degrees C. And so the problem that the student was having conceptually is they thought the heat disappeared. And the first law of thermodynamics says the heat is neither created, energy is neither created nor destroyed. And so they're getting confused. Where did the heat go? The heat disappeared. The temperature didn't increase. And we're talking about heat capacities and specific heats, right? And so where did the heat go? Breaking up the hydrogen bonding interactions. You know, the solids are much stronger. They're perfectly aligned, whereas in liquid, they're still there, but they aren't optimized. Anyway, in this particular instance, this is what we think, and the way I think about this. You know, when I look at a change in energy, let's do a change in total energy, delta U. Delta U is equal to delta PE, the change in potential energy, plus the change in the kinetic energy. And so what we have here is, since the temperature didn't change, the change in kinetic energy is 0. So where the heat went into is the heat went into changing the potential energy. That's where the heat went into. Whereas if we're dealing with an object, let's take H2O liquid. If I have H2O liquid at 0 degrees C and I add heat to this, what's going to happen? Remember, delta U is equal to Q plus W. So let's just look at adding heat. If I add heat to this, then am I going to, well, what's going to happen is I'm going to get hot water. And so did the potential energy change? The potential energy doesn't change because the potential of H2O liquid is the same as the potential of H2O liquid. H2O liquid is H2O liquid. It's the same thing. But what's going to happen is the temperature is going to increase greater than 0 degrees C. And so here, when we look at the change in energy, the change in energy is delta PE plus delta EK. And delta PE in this case is 0. And so this is just heating and cooling objects. This is changing, you know, the potential energy or changing states. And so we saw this. And I keep these separate because I don't like to mix them, because if I change both potential energy and kinetic energy, I still have to keep those calculations separate. And we do that, for example, we keep the calculations separate by doing what's called a heating or cooling curve. And so if I start off with ice, let's start off with ice at minus 30 degrees C, and I add heat to this, Q. As I add heat to this, what's going to happen to the block of ice? The block of ice is going to warm up. The block of ice is going to warm up to 0 degrees C. And so here I'm just heating an object, a block of ice. We call that Q1. And I just think of that calculation. And then I think in the next calculation. In the next calculation, I keep the kinetic energy the same. I'm changing the potential energy. That block of ice is going to melt. I call that Q2. Now the equations for Q are going to be different. Here, when we're dealing with reaction process, Q is going to equal amount times delta H or delta R. I mean, not delta R, delta U. Over here, Q is equal to the amount. Now, I don't use M. A lot of people use MC delta T. If you use M, M stands for mass. So mass times C times delta T pigeonholes you. It makes you forced to use specific heat. I don't want to be forced to use specific heat. I'd like to use molar heat capacity. I'd like to use heat capacity of the object, whatever. And so these are two different equations. So here, in step 1, I handle that as one equation. Step 2, I handle that another equation. So what I do is two separate calculations if I want to do this. And then, etc. After I melt all the ice, I have liquid water. I'm going to warm up the water, and then up to 100. And once I have it hit 100, then I'm going to boil it. And then, do you remember doing this type of calculation earlier? And so you've already done this. You've already fixed the kinetic energy and changed the potential, and fixed the potential and changed the kinetic, but maybe not in that sense. And so when we do this calculation, I can't believe I was talking about something else. Then what's the easiest way of determining delta H? The easiest way is using delta H of formation. So this is a simple calculation. We'll do it. Easiest way of determining delta S is just use this. And so these calculations turn out to be quite easy, which we'll do next time, tomorrow, and then we'll see. But conceptually, understanding the table is not so easy. Yeah, I'm gonna post it. This is gonna be to the chapter 13 homework part A, because I'm gonna cover first part of chapter 13, then I'm gonna jump to chapter 15
Okay.
a little bit, and then come back to chapter 13 because.
Do you know when the chapter 13A homework will be due?
With the chapter 13 exam. The chapter 13A and the chapter 13B homework will be due at the same time. And when we have the exam.
Professor?
Yeah.
Will this be fine notebook for Latin?
Yeah, that's fine. Where did you find that?
Bookstore.
Oh, good. How much was it?
I think it was like $2.49.
Oh, that's a pretty good price.